welcome back. So today we're going to come to the high points of Perelman's work. We want to rule out volume collapse using the monotonicity of the W function. So ruling out volume collapse in Ricci flow. And I follow for most parts the presentation by Peter Topping's notes. Okay. Now, we want to talk about volume, so given a ball of radius r around some point in a Riemannian manifold with some metric G, we let V of P and R to be the volume of the ball around P of radius R, and if it matters, then we say which metric we refer to. And then the other thing we need is the volume ratio at this point. And this is the volume, right, so we can use this notation, V of PR divided by R to the n if the manifold has dimension n. And now the main theorem says that if we start from a closed smooth manifold with Ricci flow, then this volume ratio will be bounded from below by some number depending on the initial data, depending on the dimension, and depending on the time interval, as long as we have a curvature bound. So the main theorem is the following. This, of course, goes back to Perelman. Suppose Mn G of t, where t is on some finite time interval, finiteness is important, is a solution of Ricci flow. And then let G be the metric at the final time, and suppose there is, first of all, let R0 be such that we have a curvature bound on the scalar curvature, so R is the scalar curvature, and we want this to be less than R to the minus 2 inside the ball of radius R around P for all P in Mn and all R less than R0. And of course, since the manifold is closed and compact, so I should write this, Mn closed, there we can always find such an R0, such that for all R less than R0, everywhere we have this bound. Then there exists some Xi, depending on the initial metric on capital T, on the R0 and on N, and most important is that it really deteriorates as T becomes large, so there's some positive Xi such that the volume ratio is bounded below by Xi for all P in Mn and all R less than R0. Now, let me make a few remarks about this theorem. First of all, we could have, of course, assumed that the curvature bound has the form R less than some fixed constant times R to the minus 2, then this Xi will depend in addition on C. And Xi depends on C as well, so this is just a matter of notation. A second comment is that we used only here a bound on scalar curvature. In the original paper, Perelman used the assumption that the whole Riemann tensor is less than R to the minus 2. So here we give a proof which only needs the scalar curvature, as was observed by other people. Probably Perelman needed himself. And the third comment is that this assumption of that this result of non-collapsing is of course formulated in a scaling invariant way. And so this number Xi is a scaling invariant quantity because kappa is a scaling invariant quantity. So the condition survives any rescaling procedure. So any rescaling of Ricci flow will satisfy exactly the same volume non-collapse condition. And this means that in particular our enemy, the cigar that I explained to you, which is collapsed, does not satisfy this condition, can never occur as the rescaling of Ricci flow. So this implies that the cigar or cigar cross R cannot occur as rescaling of the singularity of Ricci flow. So this theorem rules out that particular rescaling of a singularity, which was one of the main worries in Hamilton's approach to the Poincare conjecture. Now, the proof goes in 3 steps. Proof in 3 steps. Recall that given metric G and the function f and tau, we had the function w of G, f, and tau was equal to the integral of 1 over 4 pi tau to the n over 2 integral mn tau times df squared plus r plus f minus n times e to the minus f d mu. This was the W functional, and we had shown this monotonicity of W. So the aim is now to show that the that if we have this volume collapse, if there is volume collapsing at this later time, somewhere at time capital T at the end of the time interval, that then we can find a test function there, test function f, at this late time, which somehow captures this collapsing and leads to a very negative W, and then propagated backwards in time means that the W is decreasing further and becomes so negative that it is more negative than it was at the initial data, which is a contradiction, ruling out the volume collapsing at the end of the time interval. Okay? So in the first step, we show that if we have this collapsing at the end of the time interval, that then there we can make the W functional quite negative. That's the first step. So step 1. We prove that for any, formulated as a lemma, for any metric G on a closed Riemannian manifold, and for any r bigger than 0, and any point in the manifold, and for any lambda positive, the following is true. We can show that mu of G, I first have to define what mu is. So let if mu of G tau is defined as the infimum over tau, not over tau, over f of W of G f and tau, where f and G and tau compatible, and we call it compatible means that 1 over 4 pi tau to the n over 2 integral e to the minus f d mu G over mn was equal to 1. So with this definition of mu, which we know is attained by some f because of the previous lecture, it holds that mu of G lambda r squared can be estimated by 36 lambda times the volume at radius r minus the volume at radius r over 2 divided by the volume at radius r over 2 plus lambda r squared by the volume at radius r over 2 times the integral of the scalar curvature the mu over the whole bar plus a term logarithm of volume at P over R divided by 4 pi lambda R squared to the n over 2 minus n. Okay? So this is a statement purely on a fixed metric, has nothing to do with Ricci flow. It's just a statement really about the W functional, saying that if you are at a certain scale, which should scale like distance squared, so if you're at a scale which is a multiple of R squared, then you can make the infimum of the W functional very small if the volume ratio is very small, because notice this essentially scales like V divided by R to the n. So this is more or less up to constants depending on lambda and pi and n. This is the volume ratio kappa. So if kappa is very small, much smaller than 1, then this logarithm is going to be negative. This is the dominant term. So, so then this thing will be pushed down into far negative territory. And we're going to apply this lemma at the end time. If at the end time we have volume collapse, then we have this very negative term on the right-hand side, making this infimum very negative at the end time. And then in the second step, we use the monotonicity of the W functional to argue that this must have then been extremely negative at the initial time, and then we use an iteration argument to show that that leads to a contradiction if the volume ratio was sufficiently small. Okay. So in the first step, we just have to prove this general fact relating the volume ratios on a Riemannian manifold to the infimum mu of the W function. And to get such an upper bound on the infimum, all we have to do is insert a good test function into the W function. So proof idea, construct good test function for W of G F at the scale lambda R squared. But it's better, it's more prudent to write this in abuse of notation as W as a functional of this phi lambda R squared, where phi is again e to the minus f over 2. So we use different notation to set up this test function, and for that rewrite this W that was on the top of this board here, rewrite this W in terms of phi. So we had this on the board before, I suppose. W in abuse of notation, I write it as a function of phi, and if I write in here, and I use tau equals lambda times R squared, then I get the W is equal to 4 pi lambda R squared to the minus n over 2 times the integral, and here now we get lambda R squared is the tau, and then we get 4 d phi squared plus r phi squared, and then we get minus 2 phi squared times log f, and then we get minus n, and the whole thing times, n phi squared, and then the whole thing d. Okay, so this is the w function of s written as a function of phi for this particular scale. And now we have to construct the test function. And well, then we assume we have one point, of course, where the volume ratio is bad. So we're going to use a test function that lives near that point. And just have to make sure it has the right. It has the right compatibility condition. But otherwise, it turns out you can be rather simple. Often you have to sort of choose very sophisticated, say in the proof of the Yamabe problem, you have to choose a very, very delicate test function locally, which looks like the Green's function of a certain problem or so. Not here. Here you get away with a rather simple test function, namely the characteristic function cut off in a ball of radius r. So for that, let psi be just a smooth real function on the real line, non-negative, between 0 and 1, such that psi is equal to 1 on the interval up to 1/2 and 0 outside 1, and then we want psi dash, say, less than 3. Just a smooth cutoff function. And we then simply apply it to construct our test function phi. We just apply it to the distance function. So we put a constant in front, e to the minus some constant, times psi of the distance function to a given point p, divided by r, and choose c in r such that the integral of phi squared d mu times 1 over 4 pi lambda r squared to the n over 2 is equal to 1. So c is just a constant, making sure that our compatibility condition between the metric, the scale, and the function phi holds. Now, once you make that assumption, then you get from here, of course, you get that let's see. You get that e to the c times this should be e to the minus c over 2, and then you get e to the c times integral phi squared d mu, and these integrals obviously just run over the ball of radius r around p. This must be equal to let me see. Right, if I this must be less than, afterward, less than v p of r. Is this correct? If I take the integral, yes, if I put this on the other side and I square it, I get this, and then if I integrate it, the right-hand side is psi will be less or equal than 1 and equal to less than 0 outside the ball, so we get less than the volume of the ball in radius r. And similarly, we get that since psi is greater equal to 1/2 and greater equal to 0 on the inner ball, we get that this is greater than the volume of the ball at radius r/2, because that's where psi is equal to 1. So we get this condition. And now I can divide by this and get just e to the c. So I get from here, I get that v pr over 2 divided by 4 pi lambda r squared to the n over 2 is less than e to the c, and this in turn is less than v to the p to the radius r divided by the same constant. Okay, so we know exactly what this constant c is. It is in between these two volume ratios with these constants attached to them. Okay, so if this setup of our test function, we now have to compute this w, and we want to estimate all these terms from above. And let's do it term by term. So this is term 1, this is term 2, this is term 3, and this is term 4. Okay, so we have to estimate these 4 terms all from above. Now, the first term is the term 4 pi lambda r squared to the minus n over 2 times integral lambda 4 r squared times gradient phi squared d mu, and phi only lives on the ball around p. So now the gradient of phi squared, so this is less than right, so let's see what we get. We get 4 pi lambda r squared to the minus n over 2 times the gradient of phi. This gives us an e to the minus c from here, because we have to square it, then the gradient of psi gives us a the gradient of psi gives us a 3 squared, so this gives us a 9. And then the gradient of the distance function is of course less than 1, but here we get a 1 on r, and we square that, kills the r squared here, so we're left with the 4 lambda times 9 is 36 lambda. And then we are left with the volume of the ball of radius r, but the gradient doesn't live on the volume of half the radius, because that's where phi is constant, equal to 1/2. So here I only have to take the volume of radius r minus the volume in the ball of radius r over 2. So we get those terms, and then I can use this estimate here, e to the minus c is less than the inverse of this, then this cancels exactly this prefactor. So using this inequality here, the first one, turning it around, e to the minus c, cancels this factor, and I just get this thing here, 36 lambda times volume at radius r minus the volume at radius r over 2, divided by the volume at radius r over 2. Okay, that's the first term. Now, the second term is rather simple. The second term was just the same prefactor, 4 pi lambda r squared to the minus n over 2 times the integral of lambda r squared times r times phi squared d mu over the ball of radius r around p. And well, this we just estimate by the phi squared gives me an e to the minus c. The e to the minus c cancels again the term here, when I bound it from above, cancels the prefactor. So I'm just left with lambda r squared, and in the denominator I get again this v at radius r over 2, and I'm left with the integral of r d mu over the ball of radius r around p. Right, that's the estimate on the second term, rather straightforward. The most interesting one is, of course, the next term, and for that we have to use Jensen's inequality again to deal with the logarithm. So the third term had the form 4 pi lambda r squared to the minus n over 2 times the integral of minus 2 phi squared log phi d mu. Now I'm going to write this brutally in the form integral g of sigma d mu tilde. And this is again over the ball of radius r, where the new measure incorporates the prefactor. So we just put this prefactor into this measure, and we let sigma be the function phi squared, and then, by the way, we can write this as minus phi squared log phi squared. Right? So you can minus phi squared log phi squared, you can put the 2 on top there, and then you see that this g of sigma, g of y, is just a minus y log y. And then we can write it write this integral in this simplified form with a function y which is concave, because g dash of y is differentiating this is minus 1, and differentiating this minus log y, such that g double dash of y is equal to minus 1 on y, which is less than 0. So it's a concave function. So I can apply Jensen's inequality, which tells me that the average of the integral is less than the function of the average. So integral g of sigma d mu tilde is, and this is over the ball, P is less than the function of g of the integral average of sigma d mu tilde, again taken over ball r. Now, but in our case, notice that our compatibility condition means that the integral of sigma, which was phi, integral phi squared, d mu tilde, because the d mu tilde is the renormalized volume, this integral is exactly 1. This is exactly our compatibility condition. So when I take the average here, the integral of sigma, the numerator is going to be equal to 1. So, so this inequality here translates into the following thing. It says that this integral, the integral of g sigma, is what we originally wanted to compute, right? Integral of g sigma is exactly our original thing. So here is what we want: 4 pi lambda r squared to the minus n over 2. That's the minus 2 phi squared log phi. So this is, let's write it again, this is integral g sigma d mu tilde. So this, by this inequality, is less than the volume of bringing the denominator from this side to the right-hand side. but this is the volume with respect to d mu tilde, so this is 1 over 4 pi lambda r squared to the n over 2 times the volume of the ball of radius r. This is coming from the average. And now comes this quantity, and this quantity is g. G is equal to minus y log y. So we have to take we have to take minus y and g of and y was the I have to take the average of this thing. So I have to take first minus this thing, but the average of this thing is the integral of sigma at the top, which is 1, divided by the ball, by the measure of the ball with respect to d mu tilde, and this was, yeah, let's write it. This is this integral, and then I have to multiply this by the logarithm of the same thing, and the logarithm of exactly this quotient, the logarithm of 1 over integral d mu tilde p r p, right. And now in here we get this with a minus sign in the denominator, so putting this back up on top cancels out exactly this guy. So this is nothing else like dpr at the top, and I've cancelled this term against that term. I still have a minus sign, but the log of the inverse is minus the log of the thing, so I cancel this minus sign against this inverse. So I get dpr times the times the log of this thing, but the log of this thing is the same as the now I'm confused. Oh no, the volume in here, this is the volume of VPR, the volume gets cancelled as well. That's why I'm confused here. This, this thing here is exactly this thing here. So from here and here, this whole thing cancels. Okay? This whole thing cancels, and I'm just left with the minus sign. So I'm just left with the minus sign, but then I turn this around so I get exactly the logarithm of the integral of BRP of d mu tilde. But the logarithm of this is nothing else but the logarithm of the quotient of VPR divided by what you get from here, 4 pi lambda r squared to the n over 2. Okay. Sorry, I was a bit confusing for a moment, but you get this very simple estimate. You get exactly what we wanted, the logarithm of this thing here, and this is the term that's going to be very negative if there is volume collapse at the point P. Okay? And then it remains only to estimate one more term, and that last term was 4 pi lambda r squared to the minus n over 2 times minus n phi squared d mu over b over the ball. And now this is of course exactly our compatibility condition, gives us a minus, so this is exactly minus n. And now just put it together, 1, 3, 4, and 1 plus 2 plus 3 plus 4 lead exactly to the claim of the lemma. Okay, so now we have related the W functional. We found one good competitor for the W functional, telling us that it is rather negative. If there's some kind of volume collapse. Now this step 1, we are now going to apply in the second step in the following way. Step 2. We make a particular choice of lambda. Just choose lambda to be 1 over 36 in order to make that one estimate look cleaner. But I think the lemma is useful in its own right, so it's worthwhile stating it with general lambda. And the metric we're going to apply the lemma to is the metric at the end of our time interval. Because that's where we want to prove that the metric is non-collapsed. Of course, capital T in the end can be any time during the evolution. Typically, you want to apply it, say, a sequence of times approaching a singularity, because on that sequence of times you need your non-collapsing estimate to get a compactness result and prove that you get a limit. So, but you can apply it to any finite t at the end of such a time interval, and then applying the lemma, this means that the mu of g of t with lambda equals 1 over 36, so we have 1 over 36 r squared is less than, since it's the infimum at that time over all phi, it is less than what we get for this one particular phi that we just computed. And then we get with this particular choice of lambda. And here I even throw away the negative term that I was subtracting here. Even for this application I throw it away and just use the volume at radius r. And the other term was r squared divided by v over at the radius r over 2 times the integral of r d mu. And then we had the logarithm term, and now the logarithm term we had on the right hand side, to show this to you again, this was this term here, which has in the denominator the r to the n. So v over r to the n is exactly the logarithm of the volume ratio, and then from the logarithm of the 4 pi lambda, 4 lambda is 1 over 9, so we get here minus n over 2 times the log of pi over 9. And then there was still a minus n in the estimate. Right, that's what we get. Now, now we use the fact that this infimum is actually attained by some smooth function. In other words, we are now not using the phi that we had just constructed and propagated back in time. We are now saying, okay, at this time capital T, we know the infimum is at least that small, but let's now take the actual minimizer. And we did prove last time that on any closed manifold, you can minimize the W functional. So this infimum, this mu, is actually attained. So let Ft be the minimizer of W with respect to the metric at capital T over all functions here at the scale 1 over 36 r squared. This minimizer exists, so we get that this mu of gt 1 over 36 r squared, this scale, is equally the W functional at gt ft 1 over 36 r squared. Okay? So we have now the W functional at ft realizes this minimum, and this minimum is smaller than the right hand side. Now, we propagate it backward in time to use the monotonicity theorem on the W. So now solve. Now look at the solution of the system ddt g of t equals minus 2 times Ricci of g of t. This is our solution. We assume, in the main theorem, we assume that we have a solution of Ricci flow, and then we have to solve the adjoint heat equation for the function that's associated with f. So this was minus Laplacian of f plus df squared minus r, and then there was a term coming from the scaling plus n over 2 t tau, where ddt of tau is equal to minus 1. We solve this system, and we should, and here the tau we're going to choose is t plus 1 on 36 r squared minus t. Okay, so we start at when we start at this yeah, we can solve this because it's a backward heat equation. Okay, with 8 points, yeah, with f at time capital T is ft. Right? I mean, we already know that this tau solves, of course, this equation. We know we have solution of Ricci flow. This is something we have to solve in addition. So we use our knowledge that this has a smooth solution. This has a smooth solution. So now we solve this equation. So this means with dd tau, it's a forward heat equation in tau, which means backwards in t. So forward in tau, this means initial data with respect to tau, but end data with respect to t. And we know we can solve that because the metric g of t is smooth. So in this background metric, right, remember this gradient, this scalar curvature, this Laplacian, they of course all depend on the smoothness of the metric g of t. But since the metric g of t is supposed to be a smooth solution of Ricci flow, these quantities that enter the equation of f are all completely smooth. So that's why we can solve this equation for f backwards from the time capital T. And notice that when t is equal to capital T, the tau is still a smooth positive scale. Right? So it's like we set up sort of the scale of the, as if it comes from a heat kernel which is going to be singular slightly after capital T. Yeah? So we start at time capital T, we start with a small scale, but as t gets closer to zero, backwards to zero, the scale gets larger and larger until it reaches the scale capital T plus 1 over 36 r squared. So we are sort of expanding from the late time backwards in time to we are at this tiny scale where we suspect the volume collapse, possibly near singularity, and then we go backwards to the initial time at a much larger scale. So at the initial time t equals 0, this is a huge scale, capital T plus 1 over 36 r squared. Okay? Start with a tiny scale at the end, expand backwards to a big scale. And now, well, this can be solved. And the big theorem last time, or proposition by Perelman last time, is that W of G of T F at T and at scale T plus 136 minus T decreases as T decreases to 0, which is of course equivalent that tau increases towards T plus 1 on 36 r squared. Okay? That was the big discovery of Perelman, that we have this monotonicity. But that means now that we can estimate our W at the capital T from, that we can estimate this mu at time capital T from below, but the corresponding value at times T equals 0. So we get that the W at G at time 0 and at the value F at the function F at time 0 at the scale T plus 136 r squared, that this must be less than the W at G of T F at T and scale 1 on 36 r squared. But this was the mu of g of t at the scale 1 on 36 r squared. And this had all this estimate that we proved. But now this particular w of f at time 0 is of course in turn bigger than the infimum over all those guys at time 0. So this is bigger than the mu at the initial time at the scale t plus 1 36 r squared. Okay. Now, and this only depends on the initial data and the capital T. And r squared, of course. Now, we don't know what the little r is. The little r is running in a size between 0 and r, this little r0. Note that 0 is less than r, less than r0, and r0 somehow depending on the sup of the curvature of on the sup of the scalar curvature in the end time. So we have a whole range depending on this r0. So the scale here. This thing here we had bounded below for a particular value of tau. Now when you look at that proof, it's easy to see that, that the infimum, let's call this nu, of G0 well, let's not use this notation. The infimum of mu of G0 tau, where the tau runs between some fixed tau 1 and tau 2, where 0 is less than tau 1, less than tau 2, less than infinity. This is bounded below by some constant C1, bigger than minus infinity. It's easy to see that if you have such a finite range of taus between some positive number and some finite number, that you get a uniform lower bound independent of the particular taus here. This means, so we would apply this, the tau, our tau obviously would be, we would be interested, if r runs between 0 and r0, we would be interested in t and t plus 1 on 36 r0. And since since we have, if the initial data are smooth, we know that we have short time existence, so we can always make sure that this can always interested just in the cases where the t is bigger than some t0 bigger than 0, and this t0 depends on g0. So with what we proved, we get that in this whole range of taus that are of interest to us, where the r is between r and r0, this mu is bounded away from minus infinity with a uniform constant independent of r. You can prove with a little bit more work that this constant C1 is even independent of the initial tau. Yeah, so, but this, we don't need this. Can even show that C1 is independent of how far T1, tau 1 is bigger than 0, but we don't need that here for this application if we start with smooth initial data, because then we have some lower bound on capital T anyway. Okay, so we therefore conclude that we have some fixed C1 only depends on the initial data and on capital T and on the R0. So it follows, right, and on the right hand side, where was that? On the right hand side, the mu was estimated by these terms. These are just constants again, right? These depend on n and pi, 9 and n. So I can just put them on the other side and just put one big, possibly negative constant on the left hand side. So we get that if gamma equals minus C1 plus n over 2 log pi over 9 plus n, we get that gamma is less than volume P over R divided by P R over 2 plus R squared divided by U of P radius R2 times the integral R d mu over the ball of radius P plus log of kappa volume ratio at the point P at radius R. So here on the right hand side, everything is measured with respect to the metric at the end of the time, right? But the gamma depends on the initial data and on capital T, and is completely fixed now. Independent. This is independent of little r. So now, once we have reached this step, we are essentially done, because this is bounded FA from minus infinity, and you can imagine that this term here, if kappa was going to 0, that this takes us to minus infinity. We just have to be careful about these terms, because as r gets smaller and smaller, this denominator also gets to 0 here. So we have to be slightly careful and use an iteration inequality to go from here to the final result. But really, the magic happened in the second step. Right? So the first step, I guess quite a few people knew how to do that kind of thing. The magic is that you can use the second step, the monotonicity of the W functional, to propagate the behavior sort of near the singularity at the small scale r squared at the late time, propagate that back to something that's completely under control on the initial data. Okay, now to do the iteration, I have to use the non-collapsing assumption on the curvature. We call, so step 3, we call that by assumption of the theorem, of the main theorem, we had that the that for all s in the radius up to r0, the scalar curvature was less to to s to the minus 2 and on b bs around p, and right. Right, I mean, the assumption was that this was less than r0 to the minus 2, and since r0 is bigger than s, this is less than s to the minus 2. Yeah. And if you insert this knowledge into the capital R here on the estimate, then this gives you, in the ball of radius r, this gives you exactly the r to the minus 2 that cancels this r squared. And then you get the volume divided by this. So you just get this twice. So we get that gamma is less than twice v of pr divided by v of the volume r over 2 plus the logarithm of kappa p over r. So we have a much simpler inequality. Let's call this star. This is what we want to iterate. And I just note that, of course, the volume ratio of PS, say, this is the volume of PS over S to the n. If we let S tend to 0, make the ball smaller and smaller, just because it's a smooth manifold, we get the volume in the sphere, in the ball. So this is the volume of the unit ball in Rn. Right? The n-dimensional unit ball as converges to this as s tends to 0. So as s tends to 0, we know that the kappa has to go to something finite. But we need it bounded for this whole range of r's, right? For all the r's up to the curvatures level. So, therefore, now I have to tell you what our lower bound for kappa is supposed to be. Set xi to be the minimum of, and now I take 1/2 of what I get in Euclidean space, and the number e to this gamma. And remember, gamma could be a hugely negative constant, and we even subtract 2 to the n plus 1. So this is a hugely, this is a tiny number, because gamma can be very negative, depending on the initial data. And the claim is that kappa PR is bigger than C for all these R. Well, if not, then we have kappa P of S for some S is less than C. Some S. But then we get that the log of kappa P at S is less than the log of this number, so in particular the log of the minimum of the two, log of this one. So this must then be less than gamma minus 2 to the n plus 1. On the other hand, we get from our star that gamma is less than 2 times V PR over V PR over 2. Plus the log plus this, plus gamma minus 2 over n plus 1. So I can subtract gamma from both sides. So this is the same as saying 2 over n plus 1 and divide by 2, so you get 2 over n is less than VPR divided by VPR over 2. But this can be written as VPR over R to the n divided by VPR over 2 over R to the n. And if I write this as R over 2 to the n, I have to put a 2 to the n in front here. And you see that this is the same as 2 to the n times kappa of PR divided by kappa of P R over 2. But this means, well, I did this with S, right, and rather than R, so I can write here an S. I should have written an S anyway. And then this is an S, and an S here. So the upshot is that K P of S over 2 is less than K of P over S. But then if Kp of S was less or equal than C, but then it must mean that that K, I can now iterate this, right? K, do this once more, right? So I get that Kp of S times any power 2 to the minus m for any m is less than Kp of S is less than xi. But xi was less than omega n over 2. Right, our xi was less than 1/2 of what we get in Euclidean space, whereas this guy here converges, right? If we take the volume ratio at smaller and smaller scales, if we let n to infinity, then this goes to omega n. So we get omega n less, so this is a contradiction. Therefore, it must be true that, so this assumption cannot hold, and therefore we must have that the volume ratio is bounded from below, and that concludes the theorem. Right, that's the famous Perelman theorem on prevention of volume collapse under Ricci flow. Let me finish this lecture by making a remark on how this picture looks like in mean curvature flow. So, analogies for mean curvature flow. Now, in mean curvature flow, the enemy, so first remark is the analogy of the cigar is the so-called Grim Reaper, or the hairpin, as the physicists call it. So this is the curve, which looks like this, and translates to the right, y, x, x is minus log cosine of y plus t. This is a translating solution of curve shortening flow, which doesn't change its shape, and this is of course highly collapsed. Because you have regions where there's almost no curvature, but the two planes, it looks like two planes, but they are arbitrarily small compared, close together to the radius. So, or in other words, they enclose an area between them that is tiny compared to the length of the two bounding pieces. A famous example of a sequence of collapsing minimal surfaces would be the catenoids. Where you take sort of this, a catenoid, and you take a sequence of catenoids which have a smaller and smaller hole. And that gives you a sequence of minimal surfaces that collapse to two planes. And similarly here, if you make the speed higher and higher, you get a sequence of solutions to mean curvature flow or the curve shortening flow, which is moving faster and faster, but is getting closer and closer to the double cover of a half line as you work on this parameter, and it's collapsing down to a double cover of a half line. And this thing in mean curvature flow actually occurs as the rescaling of a curve. Namely, if you look at such an initial curve, then under curve shortening flow it will shrink inside, and this will shrink more fast, but because it's immersed, this is sort of forming a cusp. And when you rescale this cusp under a microscope, you get exactly, after rescaling, you get exactly that solution over there. So the Grim Reaper, this collapsed solution, can occur as the rescaling of an immersed curve. And you can do similar examples for surfaces. Actually, the cigar in Ricci flow can also occur as a limit of so-called orbifolds, but that's different. I don't want to explain orbifolds, but it's something similar, complicated like this. So now, which is not a manifold. So the only hope is to show that this picture cannot occur by making the assumption of embeddedness. So if embedded curve, this cannot happen. And there are several proofs for this. There's a proof by Grayson in his original paper. There's an argument using isoparametric inequality by Richard Hamilton, and there is a proof by myself where I show that you can show not just that an arbitrary curve remains embedded, so it can never touch itself. You can show that even though it may be tiny, the difference, the ratio between this distance d and this length L around the curve, this you can prove they exceed such that the quotient between d and L is uniformly bounded below. And xi, just like in the Perelman work, is scaling invariant. So this is a scaling invariant inequality. So if you rescale, you see that this is preserved. And of course, on the Grim Reaper, on this picture here, this d compared to that L here in this case, the d divided by L tends to 0 as x tends to infinity. Well, if this x tends to infinity, this goes to 0. So this inequality is violated on this Grim Reaper. Therefore, if you have an embedded curve where you can prove this estimate, this non-collapsing estimate, then the Grim Reaper cannot occur. So this estimate here can replace the is sort of the substitute for the Perelman estimate in the curve case. Now, there's work by other mathematicians in the case that h is positive in higher dimensions. So if the mean curvature is positive, you can sort of look at the radius of the largest ball and look at this radius r inscribed, the inner radius at some point. And then it turns out that an inequality that the inscribed radius at some point, p, bigger than 1 over the mean curvature at the point p times some number xi, where xi is positive, is preserved. This is work by Ben Andrews, building on earlier work by White and others. But this is particularly clean, so you have sort of a non-collapsing estimate which also serves this purpose and rules out singularities like that. But The big drawback is you have to assume h greater than 0 in higher dimensions. And the problem, if h is not greater or equal to 0, how to prove a non-collapsing estimate for mean curvature flow in high dimension is completely open. So there's a big open problem to work on. There's no result that resembles Perelman's non-collapsing estimate for mean curvature flow without assuming either positive mean curvature or the one-dimensional case. Okay, that's a good point to stop this lecture. Thank you.